Okay guys, today I'm going to talk about rates of change and limits. And this is a very key topic in calculus. And I'm going to start with an example that is practical that you might understand a little bit better. So we're going to start with a graph. And I got to get this line set. Okay, so let's say that you're riding your bike. And over here you have, we're going to make a function of this. Down here it's going to be the hours that you've we'll do t hours that you have ridden your bike, and here is going to be a distance, the position function. So we'll call it s of t, and this is going to be in the miles you are from home. So we're going to put miles over here. And let's say you start out so at 0. When you start timing, you're right there at 0, and then you kind of go along like this, and anyway you end up with a function that looks something like this. So let's say that you want to figure out how your average rate of change, which the rate of change in this case is going to be, a rate is like a slope, so the average rate of change would be your average speed, because it would be miles per hour. From, let's say, after 2 hours you look down and you see that you've gone 22 miles, and then you check again at 4 hours, and you are now 50 miles from home. So those are my 2 points. And so if I want to know my average rate of change, or in this case it would be my average speed, what I'm going to do, you guys could probably all figure this out, is find the slope of this line, which we call a secant line that goes through there. So it would be the change in the y over the change in the x. And so in this particular case, it would be 50 minus 22, and we're going to put miles here to help us. And the change in the x would be 4 minus 2 hours. So let's see, my average rate of change in that time is 28 miles in 2 hours. So my average speed, or average rate of change, is 14 miles per hour. That's pretty good speed. Pretty good if you're riding your bike. Now you could find your average rate of change or average speed for any particular time. It looks like if I wanted to do it, like say from 2 hours to right here, maybe that would be like 2 3/4 hours or something, then the average rate of change looks like that would be a little bit faster, my average speed right there, probably because maybe the roads were flatter and maybe I had to go up some hills after there. So you could find out at any particular time what your average rate of change is. But let's say you want to get this secant line closer and closer, and you want to know your instantaneous rate of change at 2 hours. So you want to know how fast you're going right at that second, instantaneous rate of change. So you can see here, I would just keep drawing these secant lines, and if I could get this value to be right there and be tangent, which is crossing at one point right there, then that would be my instantaneous rate of change. Okay, so here we are again. I just made a clean drawing of probably the same picture here. And this time, except this time what I'm going to do is I'm going to put this as t. It might be 2 hours like in our example before, and t, so this would be t, and s of t would be that particular point. And then if I found another point at some distance later, sometime later, so we're going to call this distance in here some amount of hours, so this point would be t plus h for hours. And so this point right here would be t plus h, comma, f of t plus h. So the average rate of change would be the slope of the secant line right there, which would be the slope of that line, which would be f of t plus h minus f of t, whoops, I'm saying f, change this to an f, over t plus h minus t, which you can see would be the change in the y, whatever those values are, over, and if we do t plus h minus t, we get h. So if this h value here gets closer to 0, so in other words, I'm getting closer here, there's my average rate of change. If I get it down to so that the distance between t and t plus h is really, really, really small, then what we call that is a limit. So if we knew that the limit as h gets closer to 0, this is how we write this, then that would be, if I threw that inside here, then the limit as h goes to 0 of this particular function would be my instantaneous rate of change. So we need to figure out how do I find a limit as that value of h goes to 0, which can be a little bit difficult here because you can see I can't just put h in for 0 because I can't divide by 0.